Hello, everyone. Welcome to our seminar this month. Today, we have fourth-year PhD candidate Madyson Barber from the University of Northern Carolina, Chapel Hill Department of Physics and Astronomy, to give the seminar. Madyson is a planet discoverer and also stellar astrophysics unique combination, and has been working with TESS data uniquely during her PhD. She has made many famous discoveries of young planets, including still the record-holding 3 mega-year planets. I have to look up the name again. IRAS 041125 plus 2902b. And you actually heard the talk previously by Rebecca on the theoretical implementation of this planet, and Madyson discovered that planet. And many other young planets around young stars. And this is actually a topic our groups are quite interested in as well. So very exciting to hear all the new progress in the field of young planets. Take away when you're ready.
Awesome. Yeah, so just to quickly reintroduce myself, my name is Madyson Barber. I am a soon-to-be final year PhD student, scary, at UNC, where I am an NSF graduate research fellow, and I work with Dr. Andrew Mann. So I spend a lot of my time thinking about really young transiting systems and how they can be used to answer questions surrounding planet formation and evolution. So after the discovery of the first exoplanets, in the 80s and 90s and very early 2000s, the exoplanet community became very interested in discovering lots of planets and finding Earth-like planets. So these Earth-sized planets around sun-like stars at distances similar to Earth. And a very efficient way to do that is by looking at lots of stars at the same time. And so studying their brightness over time, looking for these transits, as many of you know. And because we can look at lots of stars at the same time, we can do lots of observations at once. So the Kepler mission was launched in about 2009 and stared at a singular spot in the sky for about 4.5 years, trying to catch these transits. And so while Kepler didn't find this true one-to-one system, it did find thousands of these transiting planets. And so this is the distribution of planets discovered by Kepler in period and radius space. And we generally consider this to be the mature population of transiting planets because for a variety of reasons, Kepler missed star-forming regions on purpose, and so primarily targeted these mature stellar populations. So about a gig a year and older. And so the Kepler yield enabled population level analyses of these small short period planets. And what was found was this bimodal distribution separating out the slightly smaller, rockier super-Earths versus the slightly larger, more gaseous sub-Neptunes, and this radius valley or radius gap separating the two populations. And so very naturally, the next question that was asked was, how does this split form? And so a lot of work has been done to theorize these distributions, and I will very broadly categorize them into two pathways as an example. So these are the gas dwarf formation pathway and the water worlds formation pathway. So in gas dwarfs, the radius valley is a result of my initial core mass. So if I wanted to form a super-Earth or a sub-Neptune, I would start with a planet core, allow it to accrete this large envelope of hydrogen and helium, and then that atmosphere would dissipate over time due to post-formation processes like photoevaporation or core-powered mass loss. So the difference in that final planet radius is a result of how well the core can retain its atmosphere. Versus water worlds, the resulting planet radius is a consequence of where the core formed. So if I wanted to create a super-Earth, I'd form the core interior to the snow ice line where volatiles are very rare. So things like water, they're very hard to accrete. So my planet would primarily accrete hydrogen and helium, and this would lead to a smaller planet radius. And then if I wanted to form a sub-Neptune, the core would form exterior to the snow ice line where there's lots of volatiles. I fairly easily accrete them. And then the planet would migrate inwards where it would finish up accreting hydrogen and helium. And this would lead to a higher mean molecular weight atmosphere. And so these higher mean molecular weight atmospheres are harder to blow off or dissipate during post-formation evolution. So these planet radii stay fairly steady over time. But like I mentioned, the Kepler distribution, or these models by design reproduce the Kepler distribution. So the mature transiting planets can't really tell us which of these models are quote unquote correct. But lucky for us, these models create fairly different expected planet radii evolution over time. So here's the expected radius evolution for gas dwarfs in green versus water worlds in blue. And then I have them separated by sub-Neptunes, the solid lines, and super Earths, the dashed lines. So you can see by about 100 million years or so, these pathways very heavily overlap, and you can't really distinguish which pathway the planet is on without a fairly precise mass measurement. And at these ages, those mass measurements can be quite challenging. But if we instead look towards these youngest population, so these less than about 50 million-year-old planets, you can see that the pathways are most divergent, and we would require fewer planet detections to say something statistically significant about the population in these ages. And in the past few years ago, or few years or so, and really thanks to the launch of TESS, a lot of work has been done to find these young systems. So here I've plotted the distribution of young systems when I started doing research as an undergrad in January of 2020. These are the circles colored by their age. And then as we step through time, we can start to see this distribution fill in. So we can see that the youngest planets do tend to sit high in comparison to the Kepler distribution, and really even in comparison to slightly older young planets. So this may be suggestive of a gas dwarf-dominated universe. These planets will shrink with time and become uniform with the Kepler distribution. Or we could be seeing some mixing of gas dwarfs and water worlds, because we do still see some of these really young planets at this more intermediate radius, this more 3 to 5 Earth radii. But because we do see some of these really young big planets, that at least points to gas dwarfs as being a viable pathway of planet formation. So the question then becomes, what percentage of planets undergo gas dwarf formation versus water world formation? And that is really where my thesis project picks up. So I'm running the tie-dye survey, which is a demographic survey primarily targeting these really young clusters, less than about 50 million years or so, in order to find the infant systems we need to try to answer the question, what proportion of mature small planets formed via gas dwarf formation, and what percentage formed via water world formation? And so in order to answer this question well, we really need to be able to do very careful completeness corrections and be sensitive to the most planets possible. So we really need to push down to smaller planets, more multi-planet systems, so finding all of the planets around a given star, and push down to younger systems, so where those pathways are the most divergent. And so all of these kinds of planets can be quite challenging to find, really due to the young stellar noise. So finding planets can be quite challenging in general. The extra challenge of the stars being young adds on a little extra layer. So as with mature planets, just the pure probability the planet will be in proper alignment is really small. This has to do with how far away the planet is and how big the star is. But generally, it's about a 1% chance that the planet will be in an alignment such that we can see the transit. So already starting off challenging just based on alignment. And then planets are just really small in comparison to our stars. I think sometimes we get diagrams in our head and forget that planets are just super tiny. This is a diagram comparing the planets in our solar system to the sun. It's roughly to scale. So even Jupiter looks really small compared to the sun. And we really want to push down to more Earth-like systems, which we can barely even see on the screen. So if we were an outside observer trying to watch Earth transit, this would cause only a fraction of a percent change in the brightness of the sun that we're observing. So super teeny tiny changes. And then specifically for young stars, we see this noise. Young stars are just super noisy. Young stars have a lot of star spots, and they will dissipate as the star ages. But in this youngest area, there's lots of star spots on the star. So these star spots are regions of cooler regions than the surrounding star, so they give off less flux. So as the star spins, it causes this large scale variability in that observed brightness. So it can be on the order of 5 to 10% or more. But this is compounded by the fact that stars, when they're young, just also spin faster. So stars will spin faster when they're young, slow down over time. So not only are we seeing this large scale variability, but it's happening at a very rapid pace. And the rotation period of the star is sometimes even shorter than the orbital period of the planet. So when we mix all of this together, we get these really teeny tiny signals amongst this large stellar variability. And then within that variability, there's also these little wiggles that look kind of like transits. So these young stars are just really good at hiding their planets. And we have to work extra hard to find them. But despite young stars being hard, it's not impossible to find planets around them. So I wanted to show off a few of the detections that we have so far that shows that we as a community have the tools that we need to overcome these hurdles and find the planets that we need to answer our questions surrounding the origin of the Radius Valley. So this first one is 2I2076e. It's home to a stellar cluster that's about 200 million years old. And I think the system does a really good job at showing how our recent advancements in light curve extraction has enabled us to push down to these smaller planet radii. So here on the left, I have our light curve extraction in purple compared to the default extractions from TESS. So this PDC SAP light curve in orange and the SAP light curves in green. The top panel is the raw extracted light curve. The middle is after the stellar variability model has been removed. And then the bottom panel is the light curve binned and phased to our detected period. And so you can see that only with our custom extraction light curve were we able to detect the transit at a high enough significance that it triggered our transit search pipelines. So the main difference between our extraction and the default extraction is how stellar noise and systematics are handled. So in the default extraction, the short-term signal is assumed to be TESS's instrumental systematics, which for mature stars, that's fine. The mature, slow, calm stars, that's all right. But when we look towards young planets, our stellar variability can be on timescales similar to or even shorter than the systematics noise. So our custom extraction handles those two signals simultaneously, and we get these nice, clean, pretty light curves. And on the right here, you can see this planet is quite small, only about 1.4 Earth radii. So it's quite small even compared to planets similarly aged. But that means we can check off box number 1. We are more sensitive to these smaller planets thanks to continued work on how we extract light curves from TESS. Cool. So next is HIP 67522c. We need to be sensitive to more multi-planet systems, finding all of the planets around a given star. So this is the second planet in the HIP 67522 system, which is about 17 million years old. And the planets sit at about a 2-to-1 resonance with one another. So in the original discovery paper, this first transit was detected. And you can kind of see why only the first one was detected. This light curve is super wiggly, especially during transit. And these transits do look to be a little more wiggly than the B planet transits. Um, but thanks to TESS continuing to observe stars, revisiting systems, we were able to take this single transit candidate detection all the way through to validation. So we can check off box number 2. We're becoming more sensitive to more planets in existing systems, thanks to TESS continued observations. And then finally, we want to be able to push down to younger systems. So this is TIDI 1b, or IRAS 0412529002b. It's a 3 million-year-old transiting planet in the Taurus-Auriga Association, part of the D4 North subpopulation. So in addition to this being the youngest transiting planet that we know of, it's also the only transiting planet known to be in a system that still contains its protoplanetary disk. So this disk is highly misaligned in comparison to the plane of the planet's orbit and the stellar spin axis, about 60 degrees misaligned. And because it's a transition disk, we see this perfect hole in the disk that allows us to see to the star and see the planet transit. So typically when we're looking for transits, if we're expecting a certain geometry, so we're expecting the star to be spinning axis on from our point of view, and then the planet crossing right along the middle of the star. So if we see a disk in the system, we're expecting that disk to be in the same plane of rotation. Think about the solar system, pretty much everything's in that pancake flat environment. So if we see a face-on disk, we're expecting a geometry more like this. The star should be rotating pole on in our point of view, and the planet going around the star. But for some reason, the star is still edge on, and it seems that the outer disk is highly misaligned from the inner system. And so we were able to recover the transit from the ground in 3 additional filters to confirm that the planet is a planet, the signal is planetary, and that it's coming from the star we think it's coming from. So it really is a planet in this misaligned system. And this becomes even more strange when we look at the wide binary companion. Once we saw this companion, we figured that was likely causing the disk warping. However, when we looked at the orbit, analyzed the orbit of the companion, it seems to be in the same plane of rotation as the planet and the stellar rotation. So still also highly misaligned in comparison to the disk. So we have the system with the stellar spin, the planet orbit, and the wide binary companion, all in this common inclination that is highly misaligned in comparison to the protoplanetary disk, which presumably was forming the system. And so it's been really fun to hear the community's thoughts and theories about how the disk became misaligned, because I honestly don't know. My best guess is that there was some sort of flyby during formation. But nonetheless, the TIDI 1b detection shows that we can push down to these really truly infant ages. And so these are just a few of the detections so far that shows that we have the tools that we need in order to find the planets needed to answer our questions surrounding the origin of the radius valley. But radii don't tell the full story. Like I mentioned at the beginning of this talk, gas dwarfs and water worlds, their pathways still pretty heavily overlap, even in slightly older young ages. So the largest of these planets are likely to be true gas dwarfs. The recent work by Tao et al., Barat et al., and Livingston et al. Showed that planets in this regime are quite low mass, despite being so large. And this is exactly what we would expect for a gas dwarf. But these planets in this more intermediate regime are a little more ambiguous. Are they deflating super Earths, gas dwarf progenitors, or are they water world true sub-Neptunes. And so if we were able to get masses on these planets, we could start to tease out which are which. And so lucky for us, there's a number of methods that we can use to help get these masses. So one method is using transit timing variations. So because young planets, multi-planet systems, tend to be found in mean motion resonance more often and show TTV signs more often than their mature counterparts, we can take advantages of these offsets between when a transit occurs and when we expect it to occur due to gravitational interactions between the planets. And so this is work that UNC undergraduate Hannah James and I have been doing, looking at the HIP 67522 system. So this plot is slightly outdated. We're wrapping up the paper right now, but it's about the same as what we're seeing. We're finding that the B planet, we can get a consistent mass with the with Picciatao's JWST transmission spectra mass result. So low masses for planet B. And we're finding a very similarly low mass for planet C. So we're very excited about this paper. We just sent it out to co-authors yesterday. So I'm very excited to share this work very soon. And so this is the beginning of a larger survey that we're doing, looking at young multi-planet systems for TTV masses. So we're calling this survey Toddlers in Resonance, haha, because they're in mean motion resonance. And they're young. So Toddlers hopes to start to fill in this mass radius diagram with young systems to determine if this preliminary sequence we're seeing in the youngest systems is statistically significant. So in this plot, I have mass versus radius versus mass, and the circles are the mature planets, and then the plus signs are planets in our solar system, and then the other shapes are the 3 young systems with a TTV-based mass. And so this distribution is kind of exactly what we would expect for gas dwarfs. The youngest planets, so these X's, the V1298 tau system, and the stars, the HIP 67522 system, are very puffy, inflated in comparison to the mature planets. And then these diamonds, these slightly older 200 million year old planets, sit right on the edge of the mature distribution. So by about 300 million years or so, the planets should be just about done deflating, and only minor changes in their planet radius is expected between then and maturity. So you can imagine if these TOI 2076 planets shrank just a little bit, they'd be right in that bulk distribution of the mature population. So we're hoping to get more TTVs on these young systems in resonance to see, is this distribution that we're seeing statistically significant? Is it just observational bias? Because with just 3 systems, we can't really be sure quite yet. Another way we can get masses is using transmission spectroscopy from the ground. So because gas dwarfs and water worlds differ in pretty significantly in their expected densities for a planet of a given radius, we can use transmission spectra to determine the class of planet. So for a given core mass, this leads to different thicknesses in the atmosphere based on how well or how tightly the planet can pull in its atmosphere. And so this leads to different strengths in those atmospheric features that we see. And then we can use the atmospheric scale height relation to determine the planet mass. So these are simulated observations for TOI 6448b, which is about an 8 Earth radii planet in about 35 million years old. And so you can see for each of these 3 cases, the super Earth progenitor in green, the sub-Neptune progenitor in yellow, and the Saturn-ish progenitor in purple. These transmission features look quite different. So I won't claim that we can do a transmission spectra mass as well as JWST observations, but from the ground, we should be able to get these classification level masses and determine what kind of planet progenitor these super young systems are. And then finally, we can use radial velocity campaigns, which has been more typical for mature systems. But because young stars are really noisy, we can't use the typical route of radial velocity campaigns. The star is just too variable, it masks the planet. But if we can combine multi-band photometric monitoring with our radial velocity monitoring, we should be better able to model out the effects of the star and pull out these little planet signals. So this is work being led by Danny Kowalkowski out of Arizona. So I won't spend too much time talking about it, but these are observations of the Tie-Dye 1 system. So on the top panel is our LCO monitoring in 5 photometric bands or 5 optical bands. And then the bottom panel is our HPF campaign combined with the Subaru campaign from the Donati et al. 2025 paper. And these are phased to the rotation period of the star. Using these observations, we're able to find a 95 percentile upper mass limit of about 30 Earth masses for Tie-Dye 1b, which is pretty much what we would expect to see, a low mass planet, another gas dwarf, which is really exciting result as well. So the better we can constrain the planet masses, the better we can tease out which formation pathway these more ambiguous planets are a part of. So combining masses and radii, we can better probe that question of what proportion of the sub-Neptune population form via gas dwarf versus water worlds. And if we can have more masses at various ages, we can start building this age-dependent mass-radius relation. And so now that we're reaching a point where we have lots of these young planets, we can start to ask further questions beyond just the distribution of planets in period and radius space. So instead of plotting planets against their radii, if we instead plot planets against their age and this sky projected obliquity angle, we see that the mature population has a large distribution of planet-star alignments. So what we're looking at here in this obliquity angle is the angle between the stellar spin axis and the planet's orbital axis. So we generally imagine systems very flat environments, but there's some deviations to this. Even in our solar system, the planets deviate around 8 degrees from one another and from the sun. But if we look towards the youngest planets in this plot, they tend to be pretty aligned with their host stars. But with many statistical surveys comparing young and mature systems, we just don't have enough of these young observations to say something statistically significant quite yet. But if we can figure out when planets become misaligned, we can start to figure out how they become misaligned. So on this plot, I've also colored in the various regions where we expect certain mechanisms to be dominant. These are very general categorizations. The specific timescales are very system dependent, depending on the masses of the system, how many bodies are in the system, things like that. But these are general rough regions. So primordial alignments in the youngest regime happen before the disk dissipates, really is interactions with the disk. And then scattering and cosi, interactions between different bodies in the system, generally happens during adolescence. And then tidal realignment is interactions with the host star, happens during maturity. So if we can calculate the obliquity angle for more of these young systems, we can figure out when do planets become misaligned, and figure out which of these mechanisms are dominant in causing that misalignment. And so our interest in this question has led us to a little bit of a side project. And this is called the SOYSAUCE survey. So stellar obliquities of young systems, atmospheres undergoing contraction and escape. I'm more focused on the stellar obliquity side of things. And UNC graduate student in our group, Isabel Lopez Murillo, is going to take over the more atmosphere side. And so we can do both of these science cases with the same data set. So when we're looking for obliquity measurements, we're looking at radial velocity deviations over the course of the transit. So we're taking spectra over the course of the transit, so we can do transmission spectra work with that same data set. So I want to show off a few of the systems, or two of the systems that we've published so far, that shows that we should be able to answer this question surrounding which mechanisms are dominant in causing star-planet misalignments within even the next few years or so. So this first system is TIC 15007085b. It's about 135 million years old. So we took radial velocities with maroon X, which is what's plotted on the left here. And we see this nice, pretty, characteristic Roster-Laughlin signal. So this wiggle is caused by the planet transiting the star, blocking a little bit of the blue shifted light, then blocking a little bit of the red shifted light, causing this very characteristic wiggle. So the top plot is the blue channel for maroon X, and then the bottom or the middle plot is the red channel. And so we also simultaneously got this partial transit from LCO, from the TESS follow-up team. And you can see there's a flare right before transit, but we were still able to use this photometric transit to help constrain the timing of the transit. So we actually scheduled this transit before we saw the TTVs in the system. So we were only expecting to see a partial detection, and this transit is even 40 minutes early from our TTV corrected ephemeris. So we got very lucky that the transit was early rather than late. But we were able to combine these two data sets to get a pretty tight obliquity angle for the B planet. And actually, after this system was published, it was pointed out to me that this is also one of the smaller planets that we have an obliquity measurement for, which is really cool. So not only is it one of the youngest systems with an obliquity measurement, it's also one of the smallest. It's really cool. So the other system that we have published so far is the tie-dye 1b. So again, we have radial velocities from maroon X here on the left, split by the red and blue channel, which for some reason between the first paper and the second paper, I switched which order they got plotted in, whatever. And then we were very lucky to get simultaneous observations of the transit in 7 photometric transits. So we had simultaneous coverage with TESS for long-term stare, which was really nice. Then we had a Muscat transit, which is 4 simultaneous filters. And then we had 2 LCO instruments on it as well, and 2 additional filters. And so when you're looking at this RM, you might notice that we missed ingress. And despite missing ingress, we have a decently tight constraint on the slope. And you should be questionable of it because that is way too tight for that data set. I have a data set that I'm hiding from you that we also used in this analysis. So we were lucky that we were also doing this long-term monitoring for Danny's work on the mass as well. And so we used this monitoring to help constrain the local slope of the radial velocities. So combining all of these data sets, we were able to get a pretty tight obliquity measurement on the tie-dye 1b transit. And so this is now the youngest system that we have an obliquity measurement for. So when we stick these planets in context with the remaining planets, we see that they're pretty aligned with their host stars and pretty much what we'd expect for systems this young. And we think we only need about 5 to 10 more observations of young systems to get their obliquity angles in order to say something statistically significant about the young versus old population. Are we seeing our planets uniformly distributed in obliquity space over all ages, or do we see some sort of time evolving distribution? And so finally, the last thing I wanted to talk about is another question we've been thinking a lot about by doing these statistical surveys comparing young and mature systems. How do we get better ages for our planets? So given that we have such a small number of planets that we're working with, we really need to be able to do careful work with the planets that we do have to make sure we're giving them the best ages that we can. So both the most precise ages and the most accurate ages. And so we're generally looking at planets in clusters so that we can get ages from the cluster. So stars are born together, travel together as they age. So if we can better determine which family a star is a member of, we can use the bulk properties of that family to determine the age of the family, and then therefore the single star and our planet. And so thanks to Gaia, a lot of work has been done over the past few years finding these clusters. So we have lots of stars that we can work with that should be amicable for finding good precise ages and have a wide variety of clusters with ages that we can use to find planets and do the statistical work with. And then since Gaia has lots of data on lots of stars, millions of stars, I am curious in how we can use just Gaia data to age stars. So one of the ways we've been approaching this question of getting better ages is doing new methods. So this is my work I did for my master's project a few years ago, looking at how can we relate variability to stellar ages. So remember that stars have more star spots when they're young, and those spots will dissipate with time. So when Gaia comes in and observes the magnitudes of these 3 stars, it's going to find different uncertainties for the stars, even if they have the same magnitude. This young star is going to have a larger uncertainty because it's more wiggly, causing more variation, versus this mature star that is pretty smooth. Its uncertainty is going to be more photometric noise rather than variability dominated. And so when we compare this excess uncertainty or this variability index for stars of various ages, we do see that the youngest stars has a higher variability index than older stars. So this is a plot of 3 histograms of 3 different groups of 3 different ages, looking at their variability index of each member. So we have the youngest group in this yellow-orange color. This is LCC, about 17 million years old. Then in blue, we have the Pleiades, which is about 110 million years old. And then in green is Praesepe, which is about 700 million years old. And so each of these groups does have this clustering of low variability index stars, clustered at about 0.2 on the x-axis. These could just be polaron stars. It could be some sort of spectral type dependence. But if we look at the distribution as a whole, they are very well ordered. And so we take the 90th percentile of the distribution of each cluster as its representative variability score. And so when we plot this variability index for groups with known ages, we see this nice sequence. And so if we combine the variability index for a group, then we can very quickly find its age in this distribution. And so we're using the 90th percentile rather than the median here, but because we found it's more robust against outliers in the group. And then since we're using Gaia data, this is really quick to calculate, and you can do it for pretty much most stars that we observe or that Gaia has observed. And so it's also very quick because we don't need to have any additional observations. So something like lithium, where you would need to observe more stars to get lithium measurements, or like something like gyrochronology, where you would need to run Lens gargles. This method you should be able to just run very quickly on existing data. And so then another way we're trying to use Gaia data to age stars is using machine learning on the Gaia XP spectra. So we're trying to see, can we pull out an age from just the spectra themselves? So here I've plotted your typical HR diagram, and it's colored by the predicted ages from my machine learning algorithm. And you can see the M dwarfs, good age sequence as pre-main sequence coming down, well-ordered ages. And then for the giants, you can see as they're leaving the main sequence, they're also very well ordered in age as well. So I'm very excited to wrap this up. We've decided to wait for Gaia DR4 to come out since it's going to come out quite soon. But I'm excited at the prospects of other ways that we can combine existing Gaia data in order to get ages for lots of stars fairly quickly. And then so finally, because different aging methods have different strengths and weaknesses, are better in some area parameter space than others, we're looking at how can we effectively combine these different methods to get a tighter age distribution for a system for these clusters. And so these are two examples of clusters in which we've done this on so far. On the left is for TOI 6448, which is part of one of the Vela subpopulations. And then on the right is for TOI 2076, which is about 200 million years old. And so you can see the different individual distributions. Once you combine them, individually they have quite a spread. But once you combine them, they get these nice tight ages. And so, like I said, if we can find better ages for our stars, we can do better statistical work comparing young and mature systems. And so not only that, but we can also start to revisit known systems and see if they have signs of youth. So a lot of work on stellar ages has really popped up over the last few years. So some of the planets that have been found don't have age estimates or don't have expansive probing towards the age. So if we can go back and revisit some of these known systems, we might find that some of them are young. And we can add them to our young population and help reclassify some of the ages of known systems. Yeah, and so I'll throw up my summary slide here. The big key takeaway is that young planets are super cool. And you should be just as interested in them as I am, as many of you are. And I think young planets hold a lot of the answers to the questions that we want to know about mature planets. And so now that we've collected a lot of these young systems, we can start to ask even more questions about them. And the population of planets that we have is so vast. There's so much we can do with it. And if we can start to nail down ages of not only the youngest systems, but even slightly older systems, and systems without known ages, we can greatly increase the science that we can do with the population of planets that we do have. Thank you.
Thank you very much. I will stop the recording now so everybody can feel free to ask questions.